Hey, this is Mr. Medic. I'm going to try to explain to you something that I discovered that explains this property that we've been shown about segments that meet outside of a circle like this. We've been told that this line segment EA, if I multiply its length times the line segment's length from E to B, this larger line segment, that it's going to be equal to the measure of line segment EC times this larger segment ED. In fact, you can see that shown right over here in this spreadsheet. If I grab this point E, even though the lengths change on each of the pieces, their product always stays the same. No matter what I do with my E here, they're always going to end up having the same product. It's this weird property here. You can even move out the line segments inside the circle and it will still produce that same property. Well, I suspected it had something to do with similar triangles, so I went out and investigated and tried to find that relationship. So the first thing I did was I drew this extra line segment in here that's called an auxiliary line, because I wanted to see that there were more than one triangle, and now I can see that there's actually two. There's this little one, this triangle EAC, that's mostly outside the circle, and then this larger one that includes triangle EAC, triangle EBD, which is mostly inside the circle. So I thought there might be a way to prove that those two triangles were similar, and as it turns out there is. But let's go back to what the book says to us. The book says that we've got this relationship. I'm going to, just for convenience sake, label these lengths with a single letter. So this length is going to be length A, this one's going to be length B, this one's length C, and this one's length D. So the book tells us that A times this whole length, A plus B, is equal to C, which is this outside length, times this whole length, which is C plus D. And I've been telling students that an easy way to remember that is the outside times the whole is equal to the outside times the whole. Or you could say the outside times the outside plus the inside is equal to the outside times the outside plus the inside. Okay, but why is that true? Well, it must be true because there's some similar triangles. We just have to figure out what those similar triangle relationships are. Well, in order to prove two triangles are similar, all I have to do is show that two pairs of angles are congruent. Both the little triangle and the big triangle share this angle E. So that's one angle already taken care of. Now all I got to do is prove one more pair of angles are congruent. So it doesn't look like, if I grab this thing and start manipulating it, it doesn't look like this angle here is congruent with this angle here. See, if I manipulate this, you can see they don't look alike at all. In fact, that one right now, that one's obtuse and this one's acute. So they can't possibly be congruent. So what really is going on, at least I thought, was that this angle ECA is congruent to angle ABD. And as it turns out, that is the case. Now I had to prove it, but before I did that I wanted to measure it. I suspected that that measure was congruent, so I'm going to use this measurement tool to figure that out. So here's me measuring angle ECA. Measurement tool is being a little bit particular right now. ECA, there we go. Now I've got that measurement. It's nice that this tool will measure it that very easily. And DBA, there we go. And wow, they're both 80.41 degrees. And that seems to be true even when I manipulate the triangles around. I still get those same measurements. They are exactly the same. So I think those two are congruent. Now, can we argue that they are? And you know, when you're asked to make a proof, this is often the kinds of thinking you have to go through. First of all, this angle over here, this angle ACD, it's supplementary to angle ACE because this is a linear pair. So that helps me with one thing. Now this property, the next one I'm going to tell you about, is a little bit more complicated. This is a quadrilateral that's inscribed in a circle. When that happens, opposite angles like this one and that one are supplementary. So that means this angle over here, this green angle, and that green angle are both supplementary to this angle in here. We also learned that if two angles are supplementary to the same angle, then they must be congruent. Therefore, these two green angles have to be congruent because of that property. So we've actually proven that now. A similar argument can be made to prove that this angle down here, this angle D, is congruent to angle EAC. Given that fact, that means that this triangle and this triangle are similar. They're similar by angle similarity. Okay, now let's go back to, before we leave this diagram. Now notice that in the small triangle, these two angles are on kind of opposite sides. So this one's on the right side of the small triangle, but it's in proportion, or it's congruent to the angle that's on the left side of the big triangle. And because of that, this side is going to be corresponding to this whole side over here. Okay, so now we'll go back to my little chalkboard, and we're going to write that proportion that we know must be true based on the fact that the smaller triangle is similar to the larger triangle. The triangle ECA is similar to triangle EBD. So I'm going to compare the little triangle side A to the side that it corresponds to, which is this longer side over here, which is C plus D. And then on the other side of the small triangle, we get side that's length C has to be in proportion to the side on this side, which is A plus B. Well, we are real close to this relationship now. In fact, if we do a little cross multiplying, A times A plus B must be equal to C times C plus D. And there we have it. And that age-old problem that I was having is now explained.